Let us consider a mass m in kilograms of a homogeneous or non-homogeneous object. Imagine a rock like that. That means some inner piece of matter with length capital L. And imagine the density rho is constant. In general, the total mass m will be integral, and if we introduce some coordinate x running from minus L half to L half, capital L being the total length of the rod, and the contribution of the mass is rho times dV. If rho is constant, then the mass is just rho times the total volume. And if we want to prepare some formula for non-constant rho, that means for non-homogeneous objects, then we cut the object into a large number of small pieces, and we find the mass of one single piece of the object being dm equal to rho dv, where dv is the element of the volume. And then we integrate this, and we have the total mass. If rho is constant, dv can be written as the surface of this side times dx, and then x runs from minus L half to L half. For constant rho, we can factor out rho and s, and we have integral from minus L half to L half of 1 dx, which is integral of 1, which is x. L half minus L half is L. And we have rho as L, but the area of the side times the length is the volume. And so, this is the total mass, the product of the density rho and the volume V. So, nothing new up to now. Now consider a non-constant density rho, and assume the density rho has a parabolic profile, namely at minus L half and L half it is 0. And here it is quadratic. So we can write that the rho as a function of x is some constant, the maximum value in the middle at 0, times some quadratic function that goes down, and quadratic function like that can be described as 1 minus x squared. But we want to divide or multiply x with some constant so that it is equal to 0 for x is L half. So instead of 1 minus x squared, we could use 1 minus x divided by L half squared. Because then, when x is equal to L half, this fraction is 1, 1 squared is 1, and 1 minus 1 is 0, and that's what we want, the density to be 0 at the endpoints. So we want the density rho to be some constant rho 0 times this expression, 1 minus bracket x divided by L half squared. And then, in a similar way, we can find the total mass, namely integral from minus L half to L half of rho s dx, which is integral from minus L half to L half S is a constant, we can factor out S in front of the integral, and rho is rho 0. Rho 0 can be factored out as well, and we have bracket 1 minus x divided by L half square dx. At this point, substitution is useful, namely x is L half times some dimensionless variable u. If L and x are in meters, then u is dimensionless. And then the integral is s rho 0 r before the integral, and then this is an even function integrated over a symmetrical interval. So we can take 2 times integral from 0 to this point. When x starts at 0, u starts at 0 as well. And when x goes up to L half, then u goes up to 1. And the integrated function is bracket 1 minus, and x divided by L half is u alone. So 1 minus u squared, and dx is L half du, so we can multiply by L half, and we have du. And now we can integrate 2 divided by 2 reduce, and we have L s rho 0. And the antiderivative is u minus u cubed third from 0 to 1, which is 1 minus 1/3, which is 2/3. And we have 2/3. And now S, the area of the side, times the length is the volume, and volume times rho 0 is some, okay, I'll try this way. And if we now consider rho 0 to be related to the rho that was constant for the homogeneous rod, then this was the original mass with the constant density as in the previous case. So this is the idea, this is the main idea of the integral calculus. If the problem is difficult, then we cut the system, we cut the object, we cut the body, we cut the problem into a large number of small pieces. We find the mass of one single piece, that was this relation, and then integral accumulates all these contributions together.